And we're recording. Okay, so here it is, exam review for number 3. Exam number 3 review. So what we've done covering on this exam, which we purposely made a smaller amount of topics, right? So it just seems like we were just doing exam 2 just a little while ago, which is true, because we want to make sure that we concentrate on rigid body, kinematics, and we have angular kinematics, velocity analysis, and acceleration analysis. And we'll talk about maybe the subtopics that we might cover. So if your professor is using the same equation sheet that I am, this is the section from the equation sheet that's relevant, where we have the rigid body rotation about a fixed axis, and then we have with general plane motion coming on right here. And we also have the fundamental kinematics of angular velocity and angular acceleration that are very much analogous to what we did previously with fundamental kinematics for translation, right? So the very first few weeks of class, we had these relationships, and now we have the corollary, the analogous showing for angles instead of for displacements. And we have this relative motion equation, which is our basic, this is the main equation that we're really using to try to define what rigid body motion is. And we note that the relative velocity is in one plane is omega k crossed with the relative position vector. And we notice that we have the b with respect to a in both spots right there. And then the same thing true with the acceleration, except that acceleration relative vector is broken down into tangential and normal components, which could be for the tangential is going to be alpha k crossed with that relative position vector. And for the normal is just negative omega squared relative position vector. And we skipped over Coriolis acceleration, but the related to that is the relative. So this is like when the coordinates are transforming, when they're moving, right? When the reference system is moving, translating, we might want to be able to like include that attribute. And if it happens to be spinning as well, that causes something called Coriolis acceleration. But we didn't cover this, so it's not going to be on the exam, obviously. So the problems that I have assembled together come from these are all Coast Guard Academy exams, I believe. So the designation there, that's the semester and year in which we actually asked this problem. Some of these problems. So I really you suggest that I could either answer questions from these if you've already worked on them, or maybe you want to leave them to stuff where you can like simulate an exam yourself and then look at the solutions when they get posted and try to see where you went wrong, right? So you simulate the exam so that you're able to do them. So I have additional problems right here, and some of these I did in another video. So in my class, I think I've posted the videos from previous sessions. So wait, is this one? Yeah, okay, so these are Bedford and Fowler. I don't know why it's taking time for the slide to turn. There you go. So I did, so I have a lot of these problems all ready to go. It's like the same problem for whatever reason. It's just moving from one spot to another. That's weird. Okay, so what would you like to do today? We have, let's see who's joined us. Let's see.
I'm fine with whatever.
Fine with whatever. So we got Marco and George and Stefan. Anybody have any requests? We're doing total request live right here. Isn't that wasn't that an MTV? I don't know. You get. Well, I don't know if you know. Total request live. Was that? Let's see. We got a chat. Chat. I'm not sure right now. Let me look through my notes. Okay. Well, let me talk a little bit about some subdivisions of problems. So let me go here to camera and turn on my document camera. Is he going to do it? There you go, document camera. And I got my clipboard and I got my pencil. I got my pencil. All right. So we started out saying that we had, these are all rigid body mechanics, so I can just write that at a time. Rigid body mechanics. And we had angular kinematics. Right, so those were like something is spinning a certain amount, so we might know the delta theta, or we might want to know the angular velocity, or we might know the angular acceleration. And you got to remember that we can either have the constant velocity, angular velocity, or constant angular acceleration, or they could vary, and they could vary as a function of, well, the angular acceleration could vary as a function of time. It could also function as a function of theta, or it could as a function of omega. And we didn't spend a lot of time on this, but we did spend some time on it. Then we have velocity, right? So rigid body velocity, but we could do that by way of several things. We could do vector math. Right, so we could solve this using vector math. We could solve it using 3 diagrams. And I say 3 diagrams by that, which I mean is that we take something and we break the velocity vector into something that we want to find out, something that we know, and then something that we have as a relative thing. And we do that by way of like pinning one of the ends right here, right? So I guess this makes this A. So this this is the velocity of A. So we put the velocity of A at both spots, and then we spin this thing right here, right? So we might have like a velocity up here. So like maybe this is like the velocity of B. So this is the thing that we want to try to find, B with respect to A. And we know that this magnitude is just going to be this length LAB times omega AB. Right, so for the vector math, we actually use a cross product and i's and the j's, and we systematically go through there. The 3 diagram method, we are doing the exact same thing with this equation, but we're breaking it apart and we're looking at the angles for all of these things and piecing it together. And so breaking this in the x and the y direction, that should be a vector hat, we're able to break the thing apart, right? And think our way through. You get the same result, and if you look at it closely, you'll see that they turn out to be the exact same thing. But this way, I think, is superior in that we can kind of understand the contributions and the reason why we're getting the result we are in terms of the interplay of angular velocity and translational velocity. Because this equation right here says the fundamental thing of rigid body motion, that all motion can be represented by a combination of translation and rotation. This is the translation aspect, and this is the rotation aspect. And here we can actually see what directions everything are going. And then, but we could also use ICR. All right, so instead of doing this right here, we can find some magical location, and I probably am doing this incorrectly because I just randomly drew what the vectors were up to here, but we could have like, and of course that was a terrible direction for this thing to go. I'll write out, here's my ICR, and then I can find my ICR is going to be like that right there, right? So the velocities of these things are going to be dependent on where we find right here. So we're going to use the fact that we have like a 90-degree thing happening, locate an ICR, and then be able to find like what the other things are. But there's no corollary to that when we do acceleration, right? So acceleration, we want to be able to use vector math. We also want to be able to use the 3 diagrams. The thing that, as I mentioned before, that we have that makes this a little bit more tricky is that we have this other vectors that actually they're vectors, but they're actually components. We can think of them as components right here. So when we break the thing down, we'll just recognize that these and we actually kind of use that for this equation right here, but we recognize that these are going to have their own components. Even though they're components, we'll actually have components of components when using the 3 diagram method for right here. Whereas the vector math, we stick with the equation as it's, here we go, alpha k crossed r b with respect to a minus omega AB squared times RB with respect to A. So when preparing for the exam, you probably want to be able to, practice a couple problems this way, a couple problems this way. But a lot of times in order to do, but I should jump over here and say, to do an acceleration problem, you have to do a velocity problem. Now, most of the time when we would write exam problems, we would try to narrow it down so that, we would already do the velocity for you. Like, for instance, for this exam problem in spring of 2014, I remember I wrote this problem. I isolated this into a velocity analysis problem, right? And then I did the same problem here, but I gave them the omega instead, so that they could so that they wouldn't get this wrong simply because they got this wrong, right? But when practicing, if you're using these exams instead, right here, then these are supposed to, you could time yourself and think. Most professors are either going to ask 3 or 4 questions, hardly, and some professors only ask 2. I think Professor Faraci a lot of times only asks 2 questions. But you kind of think, well, that means I need to, divide my time into this amount. So I want to try to aim for a particular time to solve a problem. So we still have any requests now that I've just kind of vamped on this for a little bit? Any requests for a type of problem? You can just randomly pick one if you'd like. And in doing so, I'm not telegraphing what I would have choose, because I have some actually printed out that I haven't filled out. Let's see what we got. That's fine with me. Okay, random it is. All right, so like I have some of these that I filled out for class and mechanisms, and I haven't done these other problems right here. So I did. I will just go ahead and use these as my problems here. Okay, so we have angular velocity of rod DE is known right here to be 20 radians per second clockwise. Determine the position for the position shown. The angular velocity of BD and the velocity of the midpoint. And we're so a lot of times we'll call that G. And so here are what the answers are supposed to be. Let's see if we can get that to focus a little bit better. So I don't know why the scissors are out right there. Oh yeah, I opened up a box. That's why. So let's see. I start out with, because I know this right here, I'll do a quick little velocity thing right here. And so, oh, what did I say which way it was going to go? Clockwise. Yeah, it does say clockwise. Okay. So that's omega dE. And so this is velocity dE. And so we'll say the velocity dE is going to be omega dE, and I'll call it length dE. Or we could also call it R dE with, oh no, I should say, yeah, D with respect to E, right? So the D with respect to E, this could also be, I could also write it this way. So that's just going to be 20 radians per second times our 0.15. And somebody should be able to do that in their heads, but most normal people, but me, I had to type it on my calculator. And 3 meters per second, and it's going upwards. We could also see from here that this is going to be horizontal as part of that. So my first method, maybe I should try this in all 3 methods, right? So I kind of started off with the method that I would either use for the 3 diagram method or ICR. So I'm going to go to the vector. I'll do the vector one last. But for this one right here, it doesn't tell us what kind of method to use, so we can use all 3 methods. So I'll use the 3 diagram method as part of that. So I'll bring this guy down here and draw my 3 diagrams. And I'm not sure if other instructors are calling it the 3 diagram method. I'm just saying this is the method that's shown in Beer and Johnston. They show other methods too, but all right. So here is what we know. This is, I call this VDE, but it should just be VD. I don't know why I called it VDE. It's because I rushed up here. I need to unrush. VD. And I know that this guy is going to be horizontal. So in order to find the velocity of B, I write out my equation for the velocity of B, and I make it correspond with my 3 diagrams. And because I'm going to write, and that this equation is actually written for that end of the thing. So I apply the velocity that I know. That's going to be my reference, and that turns this into completely translation. So that's what this represents, was entirely translation and going vertically. And then so for the rotational aspect of it, we will pin it at the reference, and we'll look and see what happens up here. And I know if it's going to rotate, it'll be along, the velocity will be along this line of action for the relative velocity right here. So a lot of times if I don't know which direction the thing is going to rotate, what I'll do is I will, let me move this over to my other screen, by the way. I like to see what I'm what it looks like that I'm presenting. Oh, I might have just got lost. Oh, there now. Okay, hopefully it didn't get snagged. All right. So a lot of times if I don't know which direction this is going to go, or I can't reason out which direction it's going to rotate, I'll choose my positive, which would be counterclockwise by default from a right-hand rule, as my guess. But in this case, it is pretty straightforward because we know this thing is limited to go left and right. Well, right here, you know that it's going upwards, but it's not allowed to go upwards. So this one better go downwards, right? That's the logic we have to apply right here. That we better be in the downwards direction to counteract this upwards direction. So we know that omega dB, or BD, let's go alphabetical order. BD is got to be in this direction, and that's going to create a velocity of B with respect to D, which is going to be equal to, its magnitude is going to be omega BD times my length of BD. And the angle of this thing is going to be right here. Those are going to be the same. And when drawing this, it's a really good idea to avoid going 45 degrees, because then if you have a narrow enough angle, you know, if you do 45 degrees, a lot of times it's hard to figure out which angle corresponds to this known one, which we actually don't know yet. We need to actually find that. But I suggest when doing the 3-diagram method, you avoid 45 degrees and maybe even exaggerate it so that you have acute angles in places. All right, so I should have done maybe up this at the top. I'll call this angle D, for lack of a better thing, and take the inverse tangent of my rise over run, 0.25 divided by 0.6. And I get 30.96. I also don't know this length right here, which would be a good thing to know. So my length of BD is the square root of 0.25 squared and 0.6 squared. 0.25 squared, 0.6 squared. Add them together, and we get that this is going to be 0.65 meters. Okay. So what we're going to do here, since we already have the, and so this is our theta D that we're calling this theta D. I can write this out in my x direction. I could break out this equation in the x direction while looking at this right here. But actually, okay, so here let me let me change my mind. Let's say I notice that this is 0 in the y direction, and I'm going to use that because that's going to help isolate what my omega is. So in the y direction, we write 0. See, the velocity of B has no component. And then, so we write the velocity of D is entirely here, and it's vertical, so it's positive. So it's going to be 3 meters per second, and positive. And then, like I said, we had to go downwards. That's the reason why we picked this omega going in this direction. And so this one's going to be negative as drawn, and it's going to be omega BD times LBD, which we found up at the top just a second ago. But don't stop there, because it's only going to be the vertical component. So we want to, and we see that that's an adjacent. So we make go with the cosine of our 30.96. And we see that we can just solve for omega BD now. So we take a 0.6 and take the cosine and multiply it, and then we're going to divide by 3, divide 3 by it, and I get that it's going to be 5.382 radians per second. Now I would like to know my velocity of B. So I go in the X direction here. And this thing is entirely, and I'm not committing as to what direction it's going, positive or minus. All right, here is the second line on the third diagram on the right. The second line. You mean this guy right here? That's 90. Is the second line on the third? Yeah, okay. Yes. Well, why did you just drop all that stuff? Just put that anywhere. Okay, I'll pick it up right here. Next to the theta D. Yes, next to that theta D. Yeah, yeah, yeah. This is a perfectly vertical line right here. Yeah. Okay. Okay, so right here we have nothing in the X direction. And then this one is all in the positive direction. So we have, and it's going to be omega BD. I don't know why I wrote BL. 5.382, and it's going to be times our 0.65, and it's going to be times the sine of 30.96. And so we multiply that 0.65 and the 30.96 sine times the thing. And I didn't get the number I expected. No, maybe I did. Okay, maybe it'll be fine. We'll see. 1.7998. Really about 1.8, right? And that's going to be in meters per second. And hopefully I got that right. And then I could go down to my other little piece right here, taking a look at that rod. You know, I should have gotten 5 radians per second. So that's a little upsetting that I didn't get 5 radians per second. So like maybe I need to check that. Maybe they got it wrong, or maybe I made a mistake somewhere. So this is often the case that I make mistakes. So it was, I did that 20, 0.15, and so I got 3. I believe that 3, 0.65. This is a good chance up here. 0.25, 0.6. Yeah, 22.62. I rushed. I made a mistake. Yeah. How do you determine the downward direction of VBD? Is it just assumed to be between the X and Y axes? No. Okay. So in this instance right here, what I did is I took a look at the thing I wanted to get, and I saw that I know it has to be horizontal right here, right? That's because of this orientation of this thing is going to force it to go horizontally. It doesn't have any choice. The result will be horizontal. So I look and I see in this equation that I'm writing for this point right here, this is my reference because this is the translational component. This is like that thing moving this direction. So if this is going up, but this has got to be 0, this one has to be rotating clockwise so it can have a downward component. Does that make sense? Is that answering what you were asking? Okay, cool. There's a little delay in my bloop. Yeah, I make mistakes all the time like that. Just jump onto things. So I'm going to learn from my mistakes one of these days. So, okay, so there's my 22.62, so 0.65, and I need to take the cosine of that angle. I was about to multiply it. All right, so I get, this is going to be 0.6 right here, and I divide 3 by 0.6, and sure enough, I do get 5. Okay. So I put my 5 back in here. And I guess I didn't actually need to do this next step because they didn't ask, what they were actually asking me for was the velocity of the midpoint of this thing right here. So we'll do that here in a second to get the velocity of the midpoint. But it doesn't hurt to come up with the answer to this other point. That would be the typical thing people would probably ask you. 0.65. So we don't even know if this is the right answer or not. But we got 1.250 meters per second is what the answer will be for here. So for the midpoint, what we can do is we could reuse this same diagram, but that's maybe just a little bit lazy. There's no reason we can they'll make more paper. We can recycle. Go plant a tree if you feel bad about using up the paper and want to be socially conscious. I'm down with that. I like trees, but don't get a lower grade simply because you're trying to save paper. Okay, so we still have this guy right here, but we want to find it for this. This is the location that we want to get the thing. So we're going to write the same thing. We're going to write the velocity of g this time. We're going to call that point G is going to be equal to the velocity of d plus the velocity of g with respect to d. And so we're going to place the velocity of d at both locations. And we're going to pin it here. And we know that the velocity of g with respect to d has got to go in that direction because we just found it a minute ago. And we also know what omega BD is. And it's just going to be L, and we call that DG, right? That distance, which is only going to be 1/2 of this 0.65. Over here on the left, what we should do, like one strategy I like to do is just if I'm just going to find something generally, I'm just going to pick them both in the positive direction. So I think we got everything we need right here. We do want to make sure that we remember once again that this is that same angle, theta d, that was right here. And maybe I should have labeled this omega BD. And so I'm going to go in my x direction, velocity of g in the x. So I'm writing it for this point now onto this. It's going to be equal to, first off, I have 0 right here in the x direction. Here I have positive, and and it's going to be my omega. I'm not going to write out I'll just put values in here. I know it's going to be 5 radians per second. I know that it's going to be my length of this over 2, so 0.65 over 2, and then it's going to be the sine of 22.62. So I get 22.62 sine 0.65 times 2 divided 5 times, should be half of that, right? Duh, yeah. 0.625 meters per second. And then my y direction, VGY, is going to be, first off, is 3, right? We established, or 3.000. And then minus, though, so you'll see that this is minus 5.65 over 2, and then cosine of 22.62, and that's going to be equal to 22.62 cosine 0.65 times 2 divided 5 times, and then 3, and then we can subtract that, 1.5 meters per second. So our answer, velocity of g, is going to be, and they were both positive, by the way, so we were correct. That's why I drew it this way. They were both positive. We could say in the x direction 0.625 I plus 1.500 j meters per second, or I might want to go a little bit. Quite often we'll get magnitude and direction, right? So I just want to remind you that you should do the full magnitude and direction, when asked to, when given directions to do it. Make sure that we're putting those in there. So we see that the velocity of g is going to be the square root of, let me pick several sheets so I don't have that little texture underneath the thing. 0.625 squared and 1.5 squared. I think I did that, but all right. But that looks weird. Why would that be the truth? Is it really going to be 1.625? It looks weird. I don't know why that just strikes me as strange and likely some calculator error here. Yeah, okay. 1.625 just looks kind of weird to me. And maybe the theta of my, sometimes I'll write VG, write myself, is the angle of the thing. I don't know, give it some name. So it's going upwards at 1.5 and horizontally. And so 1.5 over 0.625 divided atan. Whoop, I did that wrong. 1.5, 0.625. Yeah, 67.38 degrees. So we could write the thing out as 1.625 meters per second, and it's coming upwards at 67.38 degrees. So we get a complete answer. All right, so, but that's just using the 3 diagrams. If instead we wanted to do this for, and find this using vector math, we definitely want to be able to do either method. We know that the velocity of, we start out with the velocity of b is equal to the velocity of d. Well, actually, we might want to start out doing the whole thing 1% correctly in vector math, right? If we're going to do it 100% in vector math, we would start off by wanting to know what the velocity of d was going to be. So we were given that omega dE was equal to negative 20 times, so that's going to be K radians per second. And the relative position vector of D with respect to E is going to be a negative, let's see if I get this right. Yeah, I think so. Yeah, or negative 1.5, negative 0.15 I meters. So we say the velocity of D is equal to the velocity of E plus the velocity of D with respect to E, which in vector terms is omega dE crossed with RD with respect to E. I think I got that right. So we know this is 0 right here. And so we take our negative 20K and cross it with our negative 0.15 I. And we know, and so we could rewrite that out here as negative 20 and negative 0.15 K crossed with I, and K cross I. Here's I, J, K. This is the way I usually do it right here. If I cross K into I, it's supposed to be an I, it doesn't look like an I. We use a right-hand rule and cross the K into I, and we get a positive J. So we get 20 times here, and what we're left with is a positive 3 J, meters per second, which is what we just expected, right? But this is doing it all formal-like, right? And now the next thing we want to do is try to find this piece right here. So we again write out our, well, let's do some preliminary work right here. We need our, well, I guess I'll write out the equation so I know what it is I'm going to need. I'll say the velocity of B is going to be equal to the velocity of D plus, and I'll go omega BD crossed with R B with respect to D. So I need to have a set, I'll put this, we'll just assume that it's positive. That's what we're really doing here, is we're assuming this is positive by you know, not putting a thing in there. So we've written this out generally, and then we'll write out what R B with respect to D is going to be. And looking back at this, we are going to go, B is going upwards, and it's going upwards and to the right. Okay, so they're both positive. So that's going to be 0.6 and 0.25. So it's 0.6 I plus 0.25 J, and these are meters. All right. So we should also recognize that VB is going to be equal to the magnitude and times I, right? And there's no J component to VB from our observation. So we can write out this thing. Let's go VBI, right? Writing out this equation is equal to, what do we get up here? We got a positive, we got 3.00 J, that's this thing entirely, plus our omega BE K crossed with 0.6 I plus 0.25 J right there. All right, so we distribute this thing out. And we could take some shortcuts, by the way, and you're going to be careful, though, when you do those. This is going to be K crossed with I. We just found out a minute ago that was J, though. We know that. And then plus omega BE 0.25 and K crossed with J. If we come back up to this little diagram, if we cross K with J, that's like coming that direction there. That's like coming this way with my fingers. And I note that my thumb is pointing in the negative I. So this is negative I. There's other ways to do this, obviously. I see some people like to go this way right here, IJK, and they say if you're going in this direction, it's positive. If you have to go in that direction, it's negative. So if I cross K with J to get, I get I, but I'm going the opposite direction, so I get a negative. This is another way that I've seen people do it. You can also do the cross product of the thing, although it's sort of a longer thing to do, is to take the, and I say cross product, the determinant of a matrix of these, this matrix, the determinant of a matrix consisting of this as row 2, and this is row 3, just like you did in statics, and you would come up with the same relations. So anyway, we take a look at the J direction of what we just written out here, and we see we have 0 is equal to 3 plus omega BE 0.6, right? Because that was the J component right there. And we get omega BE is equal to negative, and we get, that's just going to be 5, right? Which is clockwise, which is what we expected from our previous thing, right? Our previous solution, it just disappeared for some reason. Our previous solution shows us that, yeah, we were going clockwise, and we had 5 radians per second. I said BD. I don't know. Somewhere along the way, I messed up and started calling it BE when I meant to be BD. So I don't know where that started up. It was at the very beginning. Yeah, why'd you do that? I don't know. Why didn't anybody correct me? I don't know. Just okay. And then we didn't have to do the I direction, but we could, and we could say that VB is going to be equal to 0, but we're going to go negative here, right? We got to remember that's going to be negative, but we're going to put in the negative that we just found right here. So it's going to be a negative 5 right here and 0.25, and what we're going to end up is I think this is going to be the 5 and 0.25, right? Is the 1.25, and we get the same answer for VB. But the actual question was going to be, what is the velocity at G? Right. So what we need to do is we need to just write out the velocity of G is equal to the velocity of B plus omega B. This was the whole thing. V B D. Yeah. Okay. And crossed with R G with respect to B. So we have just about everything we need here. Well, we do need to put in what R G with respect to B, maybe write that over to the side, and we could do that kind of in our heads though, right? That's going to be 0.3 I and 0.125 J meters. So, and something we should recognize is that was negative right here, and so we wrote it up here, but we should put the thing as negative when we get to there. So like in the I direction, oh, no, I need to do it the right way. VG we don't know, so VG X I plus VG Y J is equal to VB, which we got up somewhere up high, up above. So we got VB. No. I said VB. I should have said D. Sorry. Just alphabetical order made me think that it would be using B, but it was actually D was our reference, wasn't it? D was in the lower left. It's easy to make little silly mistakes like that. All right. So let's see. The VD was our 3J, and then so plus my omega BD is at negative 5.00 K crossed with 0.3 I plus 0.125 J. So (5.3) K crossed with I, we know is positive J, plus 5.125 K crossed with J, we know is negative I. So in the I direction, we have VGX is equal to, well, nothing there from this, and we have a negative 5 times our 0.125. So it's negative though. So maybe I need to put I'll put the negative up in here. That's the negative, and that should be 0.625 positive meters per second. And then in the J direction, we get 3 plus, but here we're going to have a negative 5 and a 0.3 and 0.3 and 5. So we get a 1.5, which is the same thing that we got in the other one. As we'd expect, but that would be the vector math approach to this. But now we also want to be able to do this in ICR, right? So in ICR, this is actually a pretty easy one to do. Because we look at velocities and we go, we know this velocity is that direction. That's going to be our VD. And this one is constrained to go in that direction. So if we start drawing a perpendicular line to that and a perpendicular line to this, we can find our ICR. And then from observation here, we can see that, well, that means it's rotating clockwise, our omega BD. And just from the geometry here, this is our R, let's call it D with respect to ICR, it's just going to be 0.6. And our B with respect to ICR is going to be equal to 0.25. And from this direction, we already know that this velocity right here, VB, is going to be in that direction. So we can assume that we already got the velocity in the D direction from this thing right here, right? That we already did this little thing. It's usually our first thing to do. So we know that it's 3. So we could say, well, the velocity of D is equal to omega BD times RD with respect to ICR. So omega BD is equal to VD over RD ICR, or that's going to be 3 divided by 0.6. And then it's going to be 5 radians per second. So that was actually really quick, right? Way quicker, way quicker than this right here. And much quicker than this right here. But that's just because the geometry really made it a lot easier. And then if we want to get this distance right here, so we actually want to get this velocity. Let's get a little bit more careful than that. Let's see. I'll try to make it look perpendicular. It wasn't that bad. This is going to be the velocity of g. So we want to get what rg with respect to ICR is going to be. So that's going to be, first off, we need the distance, and that's going to be the square root of 0.3 squared, and this is 0.25, so this distance right here is 0.125 squared. So 0.3 squared and 0.125 squared, add them up, take square root, we get 0.325 meters. So we can figure out what the magnitude of VG is going to be omega BD times RG with respect to ICR, or 5, we just found, 0.325. So we end up with 1.625, which is the same thing we found in the other problem, right? Down here at the very bottom, nope, I guess at the top of this page. At the top of this page, we found that when we combined the x and the y together, that was the magnitude. Now we also want to, from this method, if we're going to give a full velocity of this thing, we need to give it the angle to it. So we need to do a little bit of a work right here. We have to put a little bit of thought into this right in there. We know that right there is going to be this angle. And so it's going to be the complement of this angle right there. Right, so this angle right here is the same as this, but right here this has to be perpendicular. So if we find this angle, we could take 90 minus this angle will give us this angle right here, which is how we should report this. Right. We could also have said that, noteworthy, that it's also this angle is also that angle right there. But you need to do a little bit of thought, a little bit of observation from the geometry of the thing. So I'm just going to call this, I'll just call it theta for now. I might well want to call it beta or something just to make it clear. But we'll take the tangent of the rise over run, which is actually going to be the same thing as this angle right in here, by the way. But let's use it for what we have right here. And that's going to be 0.125 up and 0.3. So 0.125 and 0.3, divide it, take the inverse tangent. You get the 22.62, which is, of course, what we found over before. So the actual angle is going to be 90 minus 22.62. Which is the 67.38 degrees. So our answer for this is going to be the VG is going to be 1.625 meters per second, and the angle is going to be 67.38 degrees, which is the same thing that we found from over here. Now we want to do an acceleration problem next, because we're 2 hours into that, well, 1 hour into this, and we want to make sure we cover the full bore. But if you go back to the things that I said that we needed to be able to do, vector math, 3 diagrams, and ICR, we've just looked at there and systematically broke them down. Now this, once again, this is a practical problem for an exam, because it does have the simplifying features, and those simplifying features are this one's entirely vertical, this one's entirely horizontal. So that's the kind of thing that you'll often see in exam problems. I think the vector math one takes the longest personally, but All right, so is there any questions on this? I've just been talking, blah, 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 blah. Some interaction.
Yeah, I have a quick question.
Okay, let me see. It looks like my computer might be getting a little slow, so just to be aware. My response of my browser was like really slow. All right, so who's asking? I couldn't quite see who was asking.
This is Stefan.
It's showing me that like I'm not connected or something. I just see that. Okay. Thank you, Stefan. All right.
Yeah. So my question was, I don't know if you can hear me very well, but
Yes, I can.
Okay. Are we going to be asked like specifically to do vector math or three-body diagram or three diagram method or
Yes.
something like that? We are? Okay.
Yes. That's a good question. And I think in some classes, some other classes, like Dr. Orlip has said to me before that he didn't care which way that the students did the problem. He just wanted to see that they got the solution. And I'm using Chrome right now as my browser, just Rachel. But Dr. Orlip said that he didn't care which way. I'm asking for, in one level, is because I want to see the students are able to do the thing. You use a particular, have that skill, but also makes it a little bit easier if to grade the thing so that I could kind of, and also not only, well, I mean, I could figure out what you did wrong, but to be able to compare, one student to another student to come up with the point values, I think is kind of this like one of the only fair ways to do it. So that's some of the reasoning behind asking for a particular method. All right, so let's see here. Let's pick another problem. So after the recitation, clear your cache and cookies on Chrome. I will definitely do that. Thank you for your advice. Let's see. So there's that problem. We did this problem before. This problem keeps showing itself up. These are all from Beard Johnston problems. There's another velocity. These are all velocity problems. Acceleration problems can be a bear. Ooh. Here's the problem that we just did right there for acceleration. But we might want to do one that's a little bit more complicated. All right, so we want to make it complicated to challenge ourselves, but not to make it too complicated. All right, so here's a Hibbler one, that's velocity. Here's another velocity from Hibbler. There's a velocity from Hibbler. Here's an acceleration. These are intimidating for a professor, by the way. You might get it wrong. So this one thing I don't like is that 45 is part of this, but this is challenging. We also have this is a challenging one. Maybe. I could either I'll do one of these. Which one? Let's see. We got 103 versus 106. What do you think? 103 versus 106 for acceleration. And by the way, these might be too difficult to do during, might too time consuming to do during an exam. That's one of the issues we have as professors is trying to make it so that it's doable in the time, because these are when they're done fully all the way out, these are long problems. So what do we have? Anybody? Let's have a poll. 103 versus 106. Let's see if the poll function's working here. Polling. 103. I got a 103. Let's see. Let's make our poll though. 103 versus 106. Oh no, I didn't want a third answer. 106. Let's see here. I want to remove that choice. Here, remove that choice right there. So kaboom. Did it start the poll? It didn't start the poll. Where's my poll? There it is. Wow, it's a slow response. I did something I said I would never do. I put my hair in a ponytail. I said I would never do that. Oh well. I guess that makes me a pony. Okay, so I think we're going to come out with 103. 103 seems to be the winner. I'm going to declare it. We have some of the people. Let's see. I don't know. Let's see who didn't vote. Let's see. Did Phil have is Phil still here? Oh, Phil's not here. Or Jordan. Okay. How do you do a poll on Collaborate? It's in the in that little share content little thingy. In the little box in the bottom. You might not see it because you're not a moderator, but I can make you.
No,
Boy,
no, I see it.
this thing is
Yeah.
wow. That it's really the response I have on my on my thing right now is like really slow. So anyway, I wish they could I wish you could pre-make polls and Collaborate instead of having to do it during class. Oh, I'm dying here. It might be, what is going on? No, it shows my signal's really bad. Huh. Wow. I might have to leave and come back, guys, because it's really slow. It's showing my collecting network statistics. All right. If you can still hear me, let me. Somebody give me a couple shout outs and say that you could still hear me.
I can hear you fine.
Okay. All right. So it's just that my browser is responding incredibly slow. All right. So let me go back to this one. Let's start off this. We have to do a velocity analysis, and I think the velocity analysis, the easiest way to probably do it in this is to do an ICR, I'm going to guess. Although this will be a little bit challenging because of the things. Okay. So let's start out with the ICR. I'll draw this piece. Well, no, I can find this first. And its velocity is going to be perpendicular. And also its acceleration is going to be perpendicular too, right here. So let's try that out right there. So this says the velocity of B is going to be omega AB times L AB, which is going to be 4 times 0.5, and I believe that's going to be 2, if I know that right, and that's meters per second. We'll also have the acceleration of B with respect to A, and the tangential direction is going to be alpha AB times LAB, and that's going to be 6 times 0.5, and that's going to be 3 meters per second. We'll also have the acceleration of B with respect to A in the normal direction is going to be omega AB squared LAB, or 4 squared times 0.5, which is that's 16. I could do all this in my head. Jeez. Oh man, but that was supposed to be squared. That was supposed to be squared. That's supposed to be squared. Okay, for my units. And I just got a text, and I don't know what that text is going to be. If it's anything important. No. Not important. Leave me alone. All right. And we know notably that this is 45 degrees. So this is 45 degrees right here. And I know that's 45 degrees, but I'd like to, just these are the angles that I think that you would have used or would have wanted to get from if this thing had happened to be in another position. Okay, So I want to find out my ICR from this thing right here, of that piece. This is at 60 degrees. This is at that way right here. And this helps to have a nice little ruler to do all these things. So here's the leg that is perpendicular to our VB right here. And we know that this velocity is going to be going upwards right here. So his is just going to be right here. So this happens a lot. You know, that you would just take the legs of this and find their intersection, right? We would just like take this down and take this down, and that's where the ICR is going to be. So you want to like kind of look for that. The same thing true with like a 4-bar mechanism. You could just take the two legs and you can see where they intersect here. So here's our ICR, and the only struggle that we'll have here is geometry, but this is 45 degrees right in here. This is 60 degrees. So this is actually a pretty easy ICR one to work through. So this angle right in here is going to be, so that's 45 and 60 should be 105, right? Yeah, if you turn the calculator on. Yeah, sure. I went ahead and checked anyway, though. So what is that going to make? Is that going to make 75 degrees? I think so. So that makes that 75 degrees. This length is known to be 1 meter right here. So this is going to be RB with respect to ICR. And this is going to be RC with respect to ICR. And it appears that this thing is going to rotate in that direction. So that's going to be the angular velocity of BC. And if that's rotating this way, that means that, whoops, I messed something up. I just messed something up. I totally, this happens. All right, so I made a mistake. My bad. Let me start again. That was embarrassing. All right. That right there is the direction for sure of this piece, right? So we're going to have a line that goes through this, but this is the direction of the velocity right here. So this is the direction of the line that's perpendicular to it, you big dummy. This is the ICR. Oh, you caught me. All right, so let me see the angles going on here. This should be 45 degrees right here, right? Yeah, it's got to be 45 degrees. And here is our VB. So if this is 60 degrees, this has to be 30 degrees. And if that's true, then 30 plus 45 is 75, right? So this has to be 105. Am I getting this right? You guys should have caught me in that mistake. It's all your fault. How dare you? No, that's not true. So anyway, here's our angular velocity, omega BD. Here's how you know I wasn't looking at the solution manuals, because I made that mistake right there. I'll try to think of it in that way. Here's our 1 meter. So if that's true, please don't tell me I got this messed up again. I'm just probably gonna start crying if I got that messed up again. So here's the velocity of C coming in that direction. Here's my R. This is C with respect to ICR, and this is RB with respect to ICR. I can barely read that. And so we need to use law of sines to be able to find these lengths. But it was lucky enough that these angles were pretty easy to get. ICR is can be a mess when the thing is at a really, really skewed angle. But we took geometry, right? We took trigonometry. We should be able to like figure those things out. So let me start off with, I probably want to know B first, right? So I'll take R of B with respect to ICR and divided by the sign that's opposite. And it's going to be equal to, and this is the one that I know, 1 is this length divided by the sine of 45. So I can get B ICR is equal to 145 sine divided as 1.414 times 30 sine times, so you get 0.7071. Okay, well that makes sense. This, I guess, maybe. I don't know. Yeah, I guess so. Okay, and meters. All right, so then I also want to get RC with respect to ICR, and that's going to be the sine of 105 equal to 1 over 45, sine of 45. RC with respect to ICR. All right, so there's 105 sine times, and so we end up with 1.3660 meters. Okay, so for my omega here, we could find a velocity of B is going to be equal to omega BD times R B with respect to ICR. Therefore, omega BD is equal to VB divided by RB with respect to ICR, or going to be 2 divided by 0.7071. Or 2.828 radians per second. And then if we want to have the velocity of C, that's going to be omega BD times RC with respect to ICR, or 2.828 times our 1.366. Come on, cross your fingers. Boom, we get 3.8, yes, 3.864, and these are meters per second, and that matches up with what I'm saying is the solution. And yes, I was going in that, I was saying the correct direction for that. So write it out as a vector. Remember, write these out as vectors. Get your full credit. If it says velocity, it wants a magnitude and units and a direction and a little hat, a funny little hat. And for my class, don't give me 5 sig figs, 3 or 4 sig figs. All right, so now we do the acceleration analysis, and we did, this was what we needed for that acceleration analysis. So I'll start on a fresh sheet right here. And, or at least a little bit of a fresh sheet. Let's see. Well, a fresh sheet. And I want to note this. Now, one thing I could do to start out with right here is I could turn this and this into the X and Y direction. That might help to organize myself, to be a little bit more organized. I know that I know it's going to be going to the left. I got to look at the values of this and this to see whether it's going to be pointing up or pointing down. That can help. It can be a little less confusing, especially the 3 diagram method in doing this. So just be aware that that could be a possible shortcut. And you could also do a coordinate transformation in order to be able to do that if you wanted to. You could say we take a coordinates like this right here and turn the coordinates that way right there if you wanted to. I think I will go ahead and keep them the way they are. But just be aware that that's maybe could make it seem less complicated for you, just as an extra step on here. But because I have these values here, I'm just going to go right towards this with my 3 diagram method and try to keep my angle correct as part of this. Okay, and so in writing this, I know the information about B, so that's going to be the thing that I'm using as my translation, and C is what I'm going to be writing the equation for. So I take my velocity of C, it's going to be equal to the velocity, not velocity, acceleration, my friend, acceleration of B plus the acceleration of C with respect to B in the tangential direction plus acceleration of C with respect to B in the normal direction. And so I will place what I know onto B. And I will draw that I know C has to be constrained in that direction. So, and here are my angles for this right there. Then I'm going to have 8. Well, I'll put it 8 meters per second squared, and I have 3 meters per second squared, and these are 45 degrees. So I place them in both spots. Let's see. I'm not going to label them all the way here. Maybe I'll label this one right here. 8 meters per second squared, 3 meters per second squared. And then because this one is the reference, it's the one that gets in. And I know it's going to be along that line. I do know I will be able to find out this guy right here, which I'll call the acceleration of C with respect to B in the normal direction, is going to be my omega BC squared length of BC. And I can find him. I just found a second ago that it was 2.828 squared, and the length of it is 1 meter. So I get nearly 8, and probably if I had, let's see, let's try that out here. If I had, yes, it should be 8 based on if I had not dropped some sig figs along the way. Right here, if I do this right here, I get 7.997 or something like there. But because I dropped a sig fig at the end, this is actually 8. And I also note my angle on here as part of this. I think maybe it's probably best to go this way right there. That right there is 60 degrees. Come on, focus. 60 degrees right there. Which will mean that this right here is 60, and that right there is 60. Okay, now when it comes to I know which direction this is going, right? This is going clockwise. But when it goes to the acceleration, we're not quite sure which way that it's going to go. So I'm going to choose by default, and I'll write that it's a guess that it's in that direction. And so this is my acceleration of c with respect to b in the tangential direction right here, which is equal to my alpha bd times my LBC. Sorry about that. I was still back on the other problem, which is going to be 1 right in there. And this is my, that should be my angle right there, right? This is 60, that's 60, so this should be 60 right here. Okay. So I write this out in the x direction for this point right here. And we say, okay, so let me do in the y direction first, because it's going to be 0 in the y direction. So that's always a good strategy if you have that opportunity. Otherwise, you'll have to do a lot of times like 2 equations and 2 unknowns if you have some other direction going on. But here we have the advantage. We could take 0 for that direction. All right, so here we have to make sure we do the components of both of these things, and make sure I put in a 45 right here. All right, so I start with this one right here. We note that that's going to be positive 3 times the cosine of 45 minus 8 times the sine of 45. And then for this one right here, we have this one's going to be positive 8 times the sine of 60. And then this one, I'm showing this as being positive because I chose this counterclockwise, but I don't actually necessarily know it. So we're going to have a alpha BC times 1, which I could have just left out right here, and then cosine of 60. Right, so calculating this thing out, we get 345 cosine times, that's positive, and I have 845 sine times, and I'm going to subtract that out, and then I have 8 times the sine of 60 times, and I'm going to add that to, so I get a positive value for all of these. So when I bring this over to the other side, I'm going to find that I get a negative, and I'm going to divide by the cosine of 60, divide this side, which I'm going to divide, and I get a negative 6.785 radians per second squared. And then I take my x direction, and now that's going to be the entirety of my x direction right there. So that's going to be the acceleration of c. And my positive and negative that I get here will determine whether it was going to go to the left or to the right as part of this. And once again, I take this, and these are both negative. So I have a negative 3 times, and this is going to be the sine of 45. And I know it doesn't matter because it's 45 degrees, but it's good to try to make sure that we keep that in mind in case we have problems where they're not. And then we have the negative 8 times the cosine of 45. And here we have, this is going to be also negative, and this is 8 times the, we're doing x direction, right? Yeah, so the cosine is 60. And we can often just look up to the one above and say, if that was sine, this is cosine. And then this one is finally going to do something positive. We're going to go plus And now it's going to be 6.785. Whoop, we got to be careful. My bad. It's positive up here, so we keep it as positive here, but we need to enter in a negative number because we found this negative. So the diagram is showing it as positive because we guessed positive. We need to enter this number in. So that was a potential mistake. So we have all negatives. So I think it's going to go to the left, is my guess, as part of this thing. And then times 1, I'm just as a space holder here. And then lastly, it's going to be the sine of 60. And we have our fingers crossed that we didn't make a mistake in this long problem. So we have 345 sine times 845 cosine times, we can add them together, 860 cosine times, can add them together because they're all negative, and then the last one, 6.875, take the sine of 60, multiply, add it in. Oh boy, I'm please be right. Please be right. Meters per second squared. Let's take a look. Yay! 17.7 meters per second squared, and we got the correct direction. Whee!
I have a question.
Yep.
Can you label in each part in the equation being the AB, ACB, the tangent, and then ACB normal?
Okay. I'm sorry. Yeah. Sometimes I was
No,
just looking at the clock. So no, it is, yeah, no, absolutely. So
fine,
let's
yeah.
see. This guy right here, we had this was the acceleration of. All right, so if I was going to write this out the correct way, this was the acceleration of B with respect to A in the tangential direction, but the Y component of it. This was, but it's a really good point, so I really appreciate you asking. This is the normal, and this is the Y component. This was the acceleration of C with respect to B in the normal direction, but the y component of it. And this was the acceleration of c with respect to b in the tangential direction, y component. So it's like these are the the components of the components is how they made it up. And in a similar way, all of these. So the acceleration of b with respect to a, tangential x, acceleration of b with respect to a, normal x, acceleration of c with respect to b, normal x, acceleration of c with, whoop, I just messed, yeah, no, c with respect to b, no, I got it, okay. I think I got that right. X. And if you were going to do this problem with cross products, it's a little bit more challenging. I mean, it's a little time consuming. It's but I think it's worth working through a problem or two where you practice, and especially if you have one where you know the solution, and so you're using a different method to try to get to the same place. I want you to be able to do, as I mentioned, to be able to do acceleration with the 3 diagram or with the vector math. But if I ask you one with the vector math, it's not going to be like an entirely complete problem for this, because that just takes too long. At least it takes me too long. You guys could probably handle it. All right, we got a nice 22 minutes left, so some or more. I'm willing to go longer if people are want that. But anybody got any requests? Here's a 4-bar. from Hibbler. I think this one might have no angular velocity. This one probably doesn't have an angular velocity to it, just from the observation of it. So anybody have any requests? Who we got left? Browser, hurry up. You know what it is? It's probably the people at Chegg are mad at me. That's what it is. I found a bunch of my homework problems on Chegg today. Ooh, what happened here? Oh, I need to plug my computer into. Yeah, see, it takes forever for a chat to come up and hear a blink. See, it's like bloop. Can you do problem 15.7 in the exam 3? Yes, absolutely. Thank you for asking. Let's see, where'd you go, Catman Joe? There you go. And let's take a look at the problems. Boom. Uh, 15.7. Okay. Okay. When studying whiplash resulting from rear end collisions, the rotation of the head is the primary interest. I would think so. An impact test was performed, and it was found that the angular acceleration of the head is defined by the relation alpha is 700 times cosine of theta plus 70 times the sine of theta, where this is in radians per second and theta here. Knowing that the head is initially at rest, find, so omega is equal to 0 at t is equal to 0, but also when theta is equal to 0, right? All right, so we want to find the angular velocity when, yes, whiplash does hurt. I totally agree. Although I used to go to heavy metal concerts and purposefully whiplash. So there you go. So that shows you the intelligence of youth. Let's see here. I believe if I were going to do this off the top of my head, come on. It's not responding. You bastards. Respond, damn you. Okay, so if I were to do this off the top of my head, I note that acceleration is a function of theta. So if I go to my basic kinematic equations right there, I could say that alpha is equal to omega d theta, right? You can see the mindset here. So we don't actually even need to have in the time as part of this. You won't believe what my browser is doing right now. All right, you bastards, stop that. It's really, I think, Adobe that's giving me problems right now. I think it's the people from Chegg that are angry at me, and they've taken over my computer. Like yeah, OneDrive's up to date. Okay, what are you doing? Not gonna open it up. Okay, just continue on then. Ah, there you go. Gonna open up over here. Finally, I wanted to take a peeky. It's totally fine for instructors to look at the solution. I tell myself now and then. Come on. And this is my good friend Sean Munnis, who picked out this as a practice problem, because we're like, well, we don't have enough practice problems from old exams, so let's pick out some out of the book. So that's what he did right there. Okay, so that's what I thought. So I have the right track. So what I'm going to do here is rewrite this thing out as omega d omega is equal to theta d, alpha d theta, and integrate from the beginning, right? So omega 0 to omega at some other position, and then we could have theta, original theta to theta right here, right? So we know that this is going to be at 0 and 0. That's a 0, not a theta equals theta. That doesn't make any damn sense. All right, so in this one's going to have 1/2. Well, I guess I could keep on. I need to write out the whole thing right here. Okay, so omega d omega from 0 to omega is going to be equal to integral from 0 to theta of 700 cosine of theta plus 70 sine of theta d theta. So we have 1/2 omega squared minus 1/2 0 squared, so just 1/2 omega squared. That's good enough. It's going to be equal to the integral of cosine is positive sine. The integral of sine, though, is negative cosine. So we got negative cosine of theta. And that goes from 0 to 30. You got to be careful here. So we got omega squared over 2 is going to be equal to 70 sine of 30 minus sine of 0, which is 0, right? I guess I'll write it here. Minus 700 sine of 0. No, wait a minute. Sine of 0 is, what is it? Sine of 0, 0. Yes, it is. Duh. Okay. Minus 70 cosine of 30 plus, because it's minus 70 cosine of 0, which is 1. So you get omega 2 squared, and hopefully this comes out to a positive number because we're going to take square root of this right here, right? So we do 700 sine of 30, that's, okay, it's 350. We subtract out, okay, this one goes to 0, but we need to subtract out 70 in the cosine of 30 and subtract that from it, but then add in 70. We get 359.4, and so multiply it by 2 and take the square root, and we get omega is equal to 26.81 radians per second. And that's really just a an implementation of these fundamental kinematic relationships, but in the angular versions of them. We got a request. Any requests? Taking requests. What type of will appear from older exams? Well, I said that for the most part, our the list of things that we'll look for are going to be angular velocity kinematics, right? So or angular kinematics, not necessarily angular velocity. We just did angular acceleration, but like these are similar to the problem that you just did. We might have a vector math for velocity, 3 diagrams for velocity, or ICR for velocity. And then for acceleration, we might have vector math to do acceleration, or 3 diagrams to do acceleration. I didn't emphasize, and because I think it takes up too much time, velocity triangles, but I would also have put that in there. I think it's in, the vector triangles for things can be useful. Beer Johnston does emphasize those like in conjunction with the 3 diagram method, but I've kind of like, I don't know, drifted away from doing that just because it takes extra time to present the material. So when I had to pick and choose which one I want to like try to point out, I try to steer maybe a little bit further away from the vector triangles. Did that answer the question? So you were saying what types of questions will appear from older exams? Yeah. You could also say from here, we could, if we come back to this, the organization that I tried to make when putting together these little exams is I went, here's your angular kinematics, velocity analysis, and it didn't tell you whether to use ICR or not in this. Sometimes I will say, so here's an acceleration analysis, right? So here was like an entire exam, I think. Like this one, and this one. I believe that was an entire exam. And here's from spring 2016, angular kinematics. Here's a velocity analysis, and here's an acceleration analysis. So this was probably an entire exam right here from in 2016. And then 2013, this was an angular kinematics. Here is the acceleration analysis. And I think there might have been a repeat. That's why I didn't have there. But here was another one that was angular kinematics. Here from 2014. So here was the velocity analysis. And I didn't say whether to use ICR or not in there. And then acceleration analysis. And then here were some more problems, right? So these were just some more problems to play around with. And it says either vector triangles, vector components, and by vector components we mean the 3 diagram method. And there's angular acceleration. So there's another one. Headbangers, kinematics, and then I said either any of these 3 methods. So you might see, by the way, in the posted solutions for these that people are the professors, because I think I didn't resolve them out myself. I put what the other professors did for their solutions. So just be aware when you see the posted solutions that they are based on whatever the professor felt like doing for their solution. But you can I would suggest that you try, if you know the answer to something, try it in multiple ways. The constant angular velocity. So there's another acceleration problem. So here's ones that I did in previous. I think I did some of these from Bedford and Fowler. I think I did those in another in a previous solution, a previous review session. Oh, here's like the solutions to them. So, yeah, like so this is on one of my coworkers, Coast Guard. I think this. No, maybe not. I don't remember who did this one. This is definitely Dr. Alicia Garcia's. Yes, and this is Sean Munnis. He's a good friend of mine. He worked for Tesla for a couple of years. He's working for a startup now. Alicia Garcia's and this was my problem. I like engines. It's Dr. Garcia. Dr. Garcia. Yeah. Anyway, not that you care about who these people are. Can we see problem 15125 done? Absolutely. If I can get back to it. Computer. You need to be purged of stuff. That's what you need. That's what I need to do. Come on. All right. That's the one you want right there, right? All right. So we have this thing is 60 degrees, and this thing is moving with a constant angular velocity of 16 radians per second clockwise. Okay. So let me write down the problem. Let me make a little sketch real quick of this, and so I could do it. All right, so that's like 60 degrees. That's close to that. And we're going horizontally in that direction. Just boom. Actually, I can just do this right here. Okay, good. And back up to here. Wow. You really are slow today, aren't you? There you go. All right. So this right here is 60 degrees, and it's going counterclockwise. Omega AB. So this is A, this is B, and this is problem 15125. And this is D, and this distance is going to be 6 inches. Let me take a look. Let's get a little closer there. You made it really itty bitty. Right. So that's 6 inches right into there, and this is 10 inches long, and this one is 3 inches long. And okay, so I'm going to do a little bit of maybe a little bit of geometry right here. Figure out what this angle is going to be. I'm going to call that beta. So beta is going to be the inverse tan of rise, which is going to be 6 minus 3 times the sine of 60, right? Sine of 60 is going to give me that. So that's going to give me this. Oh, no, I should make it inverse. Inverse sine, right? Because then I could just do about the hypotenuse right there. So, he did weird. He put his angles weird. Okay. Okay. I don't know why he did his that way. 3 times the 60 sine times minus, so it's 3.4, and take 10 and divide and take the inverse sine. So I get 19.89 degrees right there. That's what beta is equal to. And if I do a velocity analysis first, well, I'll do a velocity and acceleration analysis of this link to start with. So we have a velocity right here of VB is going to be omega AB times LAB, or they gave me this is going to be 16 radians per second. So this is 16 times 3, can't do that in my head. 256? No. 48. I don't know what happened there. Meters, no, inches per second. And this is constant right here, so there's no tangential, but there is an acceleration in this direction, which is going to be the acceleration of B with respect to A in the normal direction, and that's going to be omega AB squared LAB, or 16 squared times 3, and that is 768 inches per second squared. Okay. I have to go. Well, thank you, Rachel, for hanging out. Anytime. And let's see here. Okay. We have to do a velocity analysis now of this BD. So I think I'm going to try ICR on this again. I messed up that ICR before, and it's still eating at me, man. But we know we have this velocity coming up this direction right here. And it's the velocity of B right in there. Let's see here. Why is there no tangential component again? Because this is a constant velocity, right? A constant angular velocity right here. If there was an angular acceleration, then there would be a tangential one. We're talking about right here. There will be a component we have to worry about when we get to the big guy. But in this one, we don't have to worry about it. All right, so this is going to be. I'm going to exaggerate. This is a tough one because it's going to go way up high. So let me shorten the thing so I can actually fit it onto my page here. So I'm going to make the thing shorter. Make the ICR right here. So we'll try to make it look thinner too. So right here, because this one has a velocity that has to go in that direction. So here's our ICR, and let's see, for these angles right here, this is where it kills me right here. This right here, that's our beta, if you'll recall. And this angle right here, that total angle is going to be 60 degrees. So this is going to be 60 minus our 19.89 right in here. This one right here is going to be 30 degrees. And so this is whatever, 180 minus these other ones are going to be. And that right there, and that right there, this is going to be our RB with respect to ICR. This is the one we really need. And we note that the angular velocity of BD is going that direction in order to produce that. So that we actually have the velocity of this would also be in that direction. But if we take 60 minus our 19.89, we end up with, this is going to be 40.11, and 30, we add 30 together, and then we get like 70.1. Now we're going to take and subtract out 180. We should get like 109.9 degrees, very close to being 110. In fact, I'm like really tempted to think that it's 110. That's okay. This is our D with respect to ICR. So we take RB with respect to ICR. It's going to be divided by the sine of 109.9, and it's going to be equal to our 10-inch divided by the sine of 30, I think. So RB with respect to ICR is going to be 10 divided by the sine of 30 multiplied by the sine, so we get of 109 point whatever, and so we get 18, that's large, 18.80781 inches. I guess it's 10, that's fine, yeah, okay. And then so we could find that omega BD is going to be velocity of B divided by RB with respect to ICR. And so we end up getting 48 divided by 18.81. And I say that's 2.552 radians per second. All right, so he gave it to us in the in his solution there. All right, so we move over to our acceleration analysis now. Try to draw these as accurately as I can. And we know the acceleration of B. In fact, let's try to draw that down into there. And it should be, that should be 60 degrees. We know that this one has to be horizontal. So we're going to find the acceleration of D is going to be equal to the acceleration of B that we'll use as the reference, plus the acceleration of D with respect to B in the tangential direction, plus acceleration of D with respect to B in the normal direction. And so let's see, I'll apply this to both spots. And I'm going to pin it right here. And we've already established that this is going clockwise with our angular velocity, but we don't know which direction. So I'm going to of this. So I'm going to guess this is in the counterclockwise direction. So we will be able to find out what this acceleration is, though, because we have that angular acceleration already. And these angles right here. All right, and I said I was going to guess this direction, so I'll draw this up here. This is the direction for the tangential because of this. So this is my acceleration of D with respect to B in the tangential direction, which I know is to be BD times 10 inches. This is the 10-inch length right here. This guy right here, and I also have this angle right in here. I should know that this is the 19.89 degrees. This is also 19.89 degrees. And this is the acceleration of D with respect to B in the normal direction, which I know is to be BD squared times LBD. So that is going to be 2.552 squared and LBD would be 10. So I get 65.14 inches per second squared. And so now I'm ready to go to my X direction. Well, it's actually, once again, we have a situation where we have 0 in the Y direction. So we should probably start with the Y direction first. That's going to allow us to figure out what that alpha is going to be. So right here we say, using this equation for that spot right there, 0 is equal to, now we have, this is going to be negative, and this value we previously found to be 678. So negative 768, Jesus, I got that backwards. And that's going to be the sine of 60 degrees. And then we're going to have, let's see, I'm going to go to the tangential because I wrote tangential first. It's going to be positive. That was our guess in the Y direction. Alpha BD times our length 10. And then that's going to be the cosine of 19.89 degrees. And then this one's going to be negative, and it's going to be 65.14, and it's going to be the sine of 19.89. And so I'm going to alpha BD of, let's see, 60 times the sine times there. All right, so that's negative right here. This is also negative. Okay, so there's negative and negative. So that means that we actually going to get a positive. So we actually did a pretty good job of our guess was going to be correct. 19.89 sine of that times, and I'm going to add that and that together. Then I'm going to divide by 10, and I'm going to divide by the cosine of 19.89. No, oh, damn it. Yeah, damn it. 19.89 cosine. I probably just messed something up. So divided. And I get an angular, I get 73.09 radians per second squared. And so then I get in my X direction the entirety of AD. And so here we can say, okay, see it's negative 768. But now the cosine of 60. And now this is going to be negative right here. So we got a negative alpha, but we know the alpha is 73.09 and 10. And now they're going to be the sine of our 19.89. And then this last one, this is also negative, so we very negative in this, 65.14, and that's going to be the cosine of 19.89. So we get AD is cosine times right there. Flip that over, multiply that by 10, take the 19.89 and the sine times, boom, and we can put those together. And lastly, 65.14, but we're only take the 19.89 cosine of that times, we're going to add it together, and I get 693.9 inches per second squared. And I could go ahead and say that, well, I found they were all negative, so I went ahead and put my arrow right in there. And I get the same thing as Sean Munnis, and he went to MIT, so there. And he's a really great guy, by the way. That's a good friend. He named Newt Dog. That's how good of a friend he is. He named Newt Dog. Okay, I gotta go too. Hey, have a great weekend and make sure that you practice some problems. Please, 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 please solve the problems yourself. Work them through. Work on your speed. Everybody seems that's where people struggle the most. They aren't able to finish the exam. So I'm talking to myself. Hey, everybody that's still watching the video, I'm all by myself. I hope you have a great weekend as well. And I'm going to end now. I should leave you with a song. Should I leave you with a song? Happy trails to you until we meet again. Happy trails to you. Keep smiling on till then. Who cares about the clouds when we're together? Just sing a song and think about sunny weather. Happy trails to you till we meet again. Yeah, I know. I went off key a little bit there. It was a cappella, so it didn't really matter. Good night.